Hi, this is Mr. Merrill. We're going to walk through number 17 on the UT homework. So it says an Olympic skier moving at 33 meters per second down a 22-degree slope encounters a region of wet snow with some friction. The acceleration is 9.8 meters per second squared. How far down the slope does she travel before coming to a halt? Okay, so let's first diagram this picture. We'll draw it out. So we can envision a slope and we can draw our skier. This is 22 degrees. The coefficient of friction is 0.78. And this is where a motion diagram really comes in handy. If we imagine this as kind of the frictiony region of the snow, we're going to hit it with some initial velocity, and then we're going to be slowing down to a stop. And you can see from those velocity vectors getting smaller, we must have an acceleration in the opposite direction. So I apologize for this not being the prettiest thing in the world, but hopefully you can draw it out a little nicer on paper. So we have this acceleration point in the opposite direction because we're slowing down as we're going down the hill here. We're actually not given the mass of the skier, which is interesting and gives some people trouble later in the problem, but we'll just go ahead and continue like we would without thinking about that. So next we'll draw a force diagram. We'll begin by setting up our axes. So we want a positive x and a positive y axis. And we want to tilt those axes, I guess I should say, because we're on this ramp here and we want our axes to line up with at least one of the directions of the acceleration. So the acceleration is along this ramp here, and if we tilt it, that'll allow us to get around having an acceleration in the y direction. So I got to change the pens here. Okay. So we'll call this positive y, we'll call this positive x, and then we can begin drawing some of these force vectors. So the first one that I would draw is the force of gravity, and that's just going to drop straight down. We can go ahead and label that. That's a force of gravity acting on the skier from the earth. The next one that I would draw is the normal force, and that is the normal force acting on the skier, and you could maybe say the slope or the snow, so I'll just put an S there. And lastly, we want to consider the frictional force. And it'll do you some good to think about what size this vector should be. I'm going to purposely draw it pretty big here. And the last thing I'm going to do is label that, and that is the force of kinetic friction acting on the skier, again from the slope. And we can draw our components in as well. Might change the color for that just to make it a little easier to see. So this is the x component, that is the y component, and my cat decided to jump on my lap. Anyway, so this is FGX, this is FGY. And the reason I made this kinetic friction vector bigger earlier is because I realized, well, these are going to be congruent. The forces are balanced in the y direction, and because there's no acceleration in the y direction. And if we look at the acceleration based on our picture, our acceleration is pointed up the hill, which means there must be some net force going up the hill to produce or to cause that acceleration. So now hopefully it's obvious why this kinetic friction vector has to be bigger than this component, x component of the gravity, so that we add them together, we still get something left over pointed in the negative x direction. The next thing we're going to do, and this is where me and Dr. Holt vary slightly, he kind of does some of the work in the diagram. I like to separate it out. It's just a preference. You should end up with the same answer in the end. So I'm going to list the components of these forces. So for the normal force, there is 0 x component, and the entirety of the magnitude is in the positive y direction. For the kinetic friction, there is 0 y component, and the entirety of the magnitude is in the negative x direction. Now we're not going to just write Fk because we have another relationship for kinetic friction that is always true. We can say that the kinetic friction equals mu k times the normal force. That's always the case for kinetic friction. And because they earlier in the problem related us in terms of that coefficient, we want to use that relationship here. And then finally, our last force that we want to write in our component form is the force of gravity. Now remember, because this is the tilt angle of 22 degrees, that means this angle in the interior here on the far side is also 22 degrees. The x component points in the positive x direction. The y component points in the negative y direction, and it is adjacent to that angle. And that finishes off for writing these. Okay, so now we can generate two equations. This is really the same process for every single problem. That's the equation in the x, that's the equation in the y. And as I've said, if you choose to make your axes to line up with at least one of the direction, so that one of the axes lines up perfectly with the direction of acceleration, that means when you get to this step, one of these can equal 0. So as you see, the acceleration is all in the negative x direction. No part of the acceleration is in the y direction, so that means the y component of the acceleration is 0, which means we can change this to 0. Now it's just a matter of plugging in these values. So to sum up the x components, that's negative mu k Fn plus sine 22 degrees mg equals max. Over here we have Fn minus cosine 22 degrees mg. And now we can actually start to think about how to solve this problem. Most people get stuck at this point if they've never seen a problem like this. But the key comes in with looking at this second equation over here. We're actually interested in the acceleration because that's going to take us back to the motion. But to get that acceleration, you'll notice we don't have the mass and we don't have the normal force. So people sometimes will say, well, we have 3 unknowns here and only 2 equations. And I agree. But something really nice comes out if you've gotten to this point without having plugged in any numbers, if you're dealing with purely in terms of variables. And that is, if you solve this second equation in terms of Fn, which is a common step that you'll do when dealing with kinetic friction because it's related to the normal force, and you plug this relationship into this equation, so now instead of writing Fn, I'm going to write the cosine of 22 degrees plus sine 22 degrees equals max. You'll notice that every term here now has mass. Now you can only do this if every term has mass, right? In this previous step we couldn't cancel out the mass because there was nothing to divide out the mass in this first term. But now after the substitution, because every term has mass, or I can think about it as pulling out an m from both of these terms, or dividing all the sides by m, that's going to cancel out, leaving us an expression for acceleration. So at this point, you can plug in values for all the other things. You can come up with a numerical answer for acceleration, and then you can treat it like a kinematics problem. So, for instance, you have an initial velocity of 33 meters per second. It's asking for stopping distance. If you use the kinematics equation relating displacement, velocity, and acceleration, you'll be able to come up with an answer. I'm not going to do that work. I trust that you can. Okay, so hopefully that helped. The main point of that was to show you in a lot of these problems, if you get to this final stage, you can often do a substitution that cancels out the mass or something else. So be looking for those, especially if you're stuck and you can't see any other obvious stuff. Alright, thanks.